Hello, my name's Rob Norton, and in this series of short presentations I'd like to discuss the meaning of soil pH and its importance in managing crops and pastures. Soil pH is the term used to describe a soil's acidity or alkalinity, that is, whether it's acidic, neutral or alkaline, and it's a very important property of the soil. pH is a measure of the concentration of hydrogen ions. And the number we see, 5, 6, 7, etc., is a negative logarithm of the concentration of hydrogen ions in the soil solution. Because of this scale, a 1 unit change in pH means there's a 10-fold difference in hydrogen ion activity. Also, because pH is a negative logarithmic scale, a soil with a pH of 5 has 10 times more hydrogen ions in the soil than a pH of 6. Most soils are in the range of 5.5 to 8, often with acid soils in the high rainfall areas and alkaline soils in the low rainfall areas. Soil pH can be measured in a number of ways. In the laboratory, it's usually measured using an electronic pH meter, which has an electrode that's dipped into a solution of soil and water, or soil and calcium chloride. This is the standard method for measuring soil pH and is the most accurate. You can also get portable pH meters, such as those shown in the middle of the slide, but these need to be calibrated against standard solutions to ensure an accurate result. Many of you have probably seen the soil field pH test kit that's done using an indicator which is mixed with the soil and then a white powder sprinkled on top of the sample. The colour then bleeds through the powder and that colour is measured against a standard colour chart, giving an indicated soil pH. In most laboratory reports there will be two measures, one in water and the other in calcium chloride. The value in water is usually about 0.8 pH units higher than the value with calcium chloride. This means that when discussing pH and acidity, make sure you know if the values are in water or calcium chloride. In this presentation, we'll refer to soil pH as it's measured in calcium chloride. One of the reasons we'd want to know about soil pH is that particular crops and pastures are adapted to different levels of soil pH. For example, lucerne and medic are generally better adapted to alkaline soils and subclovers and white clovers. Conversely, crops like triticale and species like ceradella and some of the subclovers are better adapted to lower pH soils. In the mid-range between 5.5 and 7, most crops and pastures will grow adequately, but when the pH gets below 5 or so, particular species or specifically bred cultivars might be needed. The preference of plants to particular pH levels is more related to their tolerance of specific ions that are present at different pH values than particular preferences for the inherent soil acidity. Soil acidity affects the availability of different ions to plants. To emphasise this graph shows along the bottom axis the pH and in the vertical axis the degree of availability of particular ions. In that middle range of 5.5 to 7, most of the ions are reasonably available at good levels suitable for plant growth. But as the pH declines below 5.2, there is a decrease in the availability of phosphorus and also a decrease in the availability of molybdenum, both important plant nutrients. There's also an increase in the availability of iron, aluminium and manganese, and these three ions in particular can cause toxicity problems in crops and pastures. The other issue with low soil pH is that there's a reduced capacity to hold nutrient ions on clay, and this is because hydrogen ions dominate the colloid and it displaces other nutrients like potassium and calcium and magnesium, so they can't be held on the colloid, so reducing overall fertility of the soil. In the Wimmera CMA region, there's a wide range of soil types, and they display a wide range of soil pH conditions. In the main soils of the Wimmera CMA, we can look at them as being soda soils, which are soils that have a texture contrast, calcaresols, which don't have a texture contrast, the vertisols, which are the cracking clays, which are widespread in the cropping areas of the central Wimmera, and sandy soils, which are often associated with dunes and lakes and rivers. With soda soils, the main soil, the surface is slightly acidic and the subsoil is generally alkaline and sodic. Soda soils are widespread in the western Wimmera and in the northwest and southwest of the Wimmera as well. The calcaresols are generally in the northern Wimmera, and they have an alkaline topsoil, usually with lime present, and an alkaline and sometimes sodic and saline subsoil. Across the Wimmera, with what we'd call the traditional Wimmera plains, there are the self-mulching grey clays, which are the vertisols. Those soils are typically alkaline to neutral at the surface and become very alkaline deeper in the subsoil. There may be free lime present in the subsoil of those vertisols. These soils can hold large amounts of water and typically develop deep cracks as they dry. Sandy soils are often associated with old dune fields or associated with lake beds, such as lunettes on the east side of those lake beds. They tend to be acidic in the surface and also acidic down the profile. So that gives us an overview of where the acid soils generally occur. While soil type will give a general guide, soil pH varies across soil types and even within paddocks. Not a lot can be done to lower high pH soils. Well-adapted legumes can acidify the soil, and using elemental sulphur can also acidify the soil, but those processes are slow. More importantly, on low pH soils, liming is the way to reduce the acidity levels and so raise the soil pH. Carbonate ions from agricultural lime react in the soil solution, creating an excess of hydroxide ions, which then combine with the hydrogen ions, forming water and carbon dioxide gas. This means it neutralises some of the acidity from the hydrogen ions. Lime can also help provide calcium, which goes into the soil colloid and helps with soil structure as well. Farmer experience and long-term research has shown that farming will make soils more acidic. Soils become more acidic because of two reasons. Firstly, the removal of basic ions like calcium, potassium, magnesium in produce such as hay and grain, which leaves the farm. And secondly, soils become more acidic because of the conversion of ammonia from nitrogen fertilisers and legumes to nitrate and the subsequent leaching of nitrate down the profile, which leaves hydrogen ions behind in the topsoil. A clay loam soil in a cropping system can acidify by 0.05 pH units per year, and so in 10 years we could see half a unit pH change, and a lime requirement to meet that would be around 180 kilograms of lime per hectare per year. That pH change is not particularly problematic if the pH is between 6 and 7, but over time as pH declines it can fall below 4.4 to 4.9, which is a trigger point to consider liming to maintain crop and pasture performance. The aim of liming is to raise the pH between 5 and 5.5. To briefly review what we've discussed, firstly, pH is a measure of the acidity or alkalinity of the soil. The importance of pH is that it controls nutrient availability, and at low pH some nutrients will become less available to crops and pastures, and other nutrients can become so available that they become toxic. The only way to know soil pH is by taking good soil samples and getting them tested in an accredited laboratory. It's often a good idea to take both topsoil, 0 to 10, as well as subsoil, 10 to 30 samples to see whether the acidity is in the topsoil or in the subsoil as well. Knowing that information, you can then decide on a plan going forward for the management of your soil pH. Thanks.